Hi, welcome back. So we carry on our investigation on building up on the study of bivariate analysis. So previously we've captured our correlation variable, and it was in a percentage of minus 2.7% or something. Based on the coding mechanism, gender was 1 and 2, and the type was 1, 2, 3. So basically what this value is telling me, now when I move it from 1 to 2, it's telling me this one that the value on the type, if it was 2, it would have been 1, as if it was 3, it would be 2. So you could see there is a negative relation, and this movement is quantifying by minus 2.7, but still I don't know the magnitude and what is the real effect of having a gender, a change, and their effect on the scoring of ABC. And that's the job exactly of something called the effect size. So the effect size, it helps you to capture that magnitude of change by how much a changing of a gender can have an effect of the scoring result. Now, essentially to capture that, there's a value called the Kramer's V value. Now, to capture Kramer's value, it depends on another value they call the chi-square. And chi-square actually is a very popular name in the world of statistics and study of analysis. There is a chi-square test, there's a chi-square test hypothesis, but this chi-square particularly, it helps you to capture or to quantify similar to the variation that we capture in a continuous value, if you remember. If you look at the formula of chi-square, it's basically by taking the observed value, subtracted from its expectation, divided by the expectation square, of course, the term. Let's try to apply that knowledge on our example in here. Now, we know there were 4 males who scored A, which are 20%, but we need to calculate something, the expected value of this entry. So how to do that? By taking the value of 12, which is the total of male, multiplied by 6, and then you divide that by the total number of subjects, which is 20, and then you will get you 3.6. In this entry here, again, 12 multiplied by 7 and divided by 20, you will get 4.2. For this one here, it's 8 multiplied by 7 divided by 20. I hope these numbers are quite clear to you. So these are the expected for each entry that I have in here. Now I want to see the observed one, and this is the observed. It's 4, 6, 2, etc. So basically what I do, I take the 4 I observed, subtract it from what I expected here, 3.6, square it and divide it by, again, what you expected. It's like the variance one. You do that for each entry, and after you finish, sum up the entire numbers and you will get a number. This number, it's called the chi-square number. So basically what you do, you take the chi-square value and you divide it by the multiplication of this total number of 20 that we know it, multiplied by something called the degree of freedom. And what is the degree of freedom? It is the minimum of rows minus 1 and columns minus 1. In this case, in this example, how many rows we have? We have 2 minus 1. And how many columns we have? We have 3 minus 1. So this is 1 and this is 2. We say take the minimum between them. Of course, it's 1. If I want to apply the formula, I will get 4.868, which is a chi-square, divided by 20, which is the total number of my observation, multiplied by the degree of freedom of 1, which is 20, and you will get 0.49. This value is called the Kramer's V value. Now, how to interpret that? There is a table. It shows you small effect, medium effect, and large effect. Now, to decide is it this value is a small effect or medium or large depends on the degree of freedom you use. In this case, we use degree of freedom of 1, and our value, it's somewhere here. It's a kind of a medium effect, and I could say it's a logical and sense to make that because actually the number of subjects are only 20. Now, if it happens your table to be 2 by 2, that we use is called the phi effect, which is again the chi-square divided by the n. Now, one more last tool I'm going to share with you. It's called the odd ratio analysis. And again, when you have x1 and x2 variables to be dichotomy, for example, 0 and 1, or success and fail, something like that. Look at this example I have adapted from a study. In this example, we have 2 therapies, and then we are studying the patient to be cured or actually not cured. So you got 2 by 2 cases. For example, here could be cured as 1, not cured as 2. And here is therapy 1, like say, and this therapy 2. Now, basically, I have got 50 number of patients. Now happens to see that X1 he was successful and he used, for example, therapy 1, the other one unfortunately not successful, he used therapy 2, etc. This is how we collected the data. Now this is telling me the following: 31 they were cured who used therapy 1, and 11 they were not cured, they were using therapy 1. That means I got 42 people out of 150 they have used actually therapy 1. Now out of this 42, I know that 31 they got the result of 1, and I got 11 of them unfortunately get the result of 0. Now it's telling me when it comes to therapy 2, 108 out of 150 actually, 57 of them got the result of 1, but unfortunately 51 of them got the result of 0. Now by looking at this just by eyeing, I can tell you that therapy 2 doesn't seem to be so much promising. Now what is the odd ratio is telling you? It's giving you a probable number by how many times use of therapy 1 guarantee be cured, or using the therapy 2 can be risked not to be cured, etc. This is the language of using something called the odd ratio. Now I think the 88 is quite clear to you. It's just the sum of people who cured. 62 they were not cured. Now intuitively, if you want to calculate the effect size in the form of this odd ratio analysis, watch carefully how did we construct that beautiful table. What is the risk? 26% that there is a risk while you are using therapy 1. 47.22% if you are using therapy 2. Now how to calculate the odds? Therapy 1, you got the ratio between 11 and 31. Therapy 2, by taking the ratio of 51 people they were not actually cured out of 57 they were cured. This is the odd between them. Now if you take the ratio of the risk, you could say it's 1.8, the odd 2.52. What does that mean?
First we are going to consider our conclusion in terms of being not cured. The first value 1.8 tells us that people who use therapy 2 are 1.8 times at risk of being not cured more than those who use therapy 1. The second value odd ratio of 2.52 tells us that people who have been treated and not cured are 2.52 times more likely to be treated using therapy 2. To conclude, the odd ratio is a powerful and intuitive tool to measure kind of effect size. The only condition is required that the variable have only 2 possible outcomes.
Now we're going to move in the next step to analyze 2 variables that happens to be continuous. We are in this zone. I will see you then.